All right. How's it going, everyone? Let's get things set up here. So, welcome. If you're a new joiner, I really appreciate you taking the time to come and watch my stream. If you've been here before, equally, I appreciate you coming back, having sat through numerous other streams. So, welcome. Hope everyone's having a good weekend. Enjoying the extra hour. So today I thought we would take a look probably one last time at Emotet. And in particular, I find it quite interesting to look at the configuration of Emotet, or at least try to get access to more indicators of compromise, because it can be quite a tricky sample. And I think as well, when you run it and monitor it from a behavioural point of view and then try and pick it apart, you can go off in so many different directions. But one element I thought I'd share with you today is how to actually dump the config of C2s from Emotet, and as part of that kind of journey we'll go on over the next 30 or 40 minutes, is the mentality of approaching malware from like a malware initial assessment point of view, and then also unpacking techniques when we're looking at process injection. And then also a bit of ingenuity, hopefully, that you can apply to other samples as well, in terms of how you can actually access or go hunting for key IOCs and stuff like that. So I'll have a little play around. Hopefully, it'll be of interest to you. And then I've got tons more content that I really want to kind of cover off on these streams and stuff. So watch this space for more as well. So good, I guess. Duncan, you joined me again. I'm looking at the chat, so this is really cool. Thank you for coming back. Goran, hi. We also have Poet. How's it going? Jumbo, good to have you on board. So thank you for taking the time out of your Sundays to come and listen to me. It's really appreciated. So let's get rolling. One of the sample I wanted to kind of look at was one I saw recently, actually, in the wild, Emotet. I think it's so prevalent at the moment that almost any sample you can follow along with. But I will share the hash for this one in the video description. Let me get it onto my virtual machine here. Darren Bisbee's in the house. How's it going? Nice to see you again. This is playing silly buggers on me, so let me restart my VM. Jared in Switzerland. Yeah, cool. Thank you for joining. Righty, let's get the virtual machine cranked up. I thought I'd have a bit more time to prepare for this stream today, if I'm honest with you, but those of you who've got children, you'll understand. So, here we go. Right, let's get the baby on here now. The first thing I'd like to do, I mean, with any sample, it doesn't matter what if I'm going to kind of dive in and take a look at the inner workings and start disassembling samples, or whether I'm more interested in behavior stuff, I tend to follow the same steps for malware initial assessment, and that's just to kind of have a look. Initially, I stick it in P Studio, which if this virtual machine ever wakes up, I will show you, and then just kind of get a feel for what I can kind of expect from the malware, and then when I run it, let me do this again. It's crazy. And when I run the malware, then I look for like specific things in process monitor, right? So what processes does it spawn? Does it write files to disk? Does it, do stuff in the registry? That kind of thing, really. Which again, we'll have a quick look at, and also we'll compare what happens in the sandbox as well. So we'll have a quick look at the kind of indicators that sandboxes can give you, which probably will be very similar to what we see on our virtual machine in this particular instance. So let me get this damn sample on my VM. Otherwise it'll be a very short stream, this. See, it says it's copying, and then it kind of loses the will to live a little bit. Right. Let me have a look at my other screen, see what's going on. Alex, are you asking, am I working on a Mac? I do have a MacBook, yes, which is my main machine I'm on now. Obviously, I'm running virtual machines here to give me Windows on my Mac. At the moment, it's not very fast. What is up with it? It's crazy. Probably it doesn't help that it's an old version of VMware Fusion that I use. Every piece of software I have seems to be really outdated, but the joys of live streaming, right? Let me try my other snapshot and see if this is any better. Thanks, Masood. I appreciate your comments. What is up with my machine? Right, let's see if I can get this file on here. I know, Darren. I think I'm going to have to bite the bullet and reboot. I might actually quit VMware altogether and just reboot it. Apologies, guys. Yeah, I don't play games. Not really. I'm not averse to them. It's just, to be honest, probably more of a time issue than anything else. So, all right. One last try before I reboot. That's why I use a MacBook. Fucking Windows. It's not looking good. Let me reboot. What I will do is I stuck the sample in a sandbox just a few minutes ago, so let's talk through that quickly. Hopefully this will wake up in the background. Yeah, force, go. It's not happy. Anyway, so let me come here. So this is the sample, and again I'll share the hash on the video. Is it finished? Yeah. So I stuck it into reverse it or hybrid analysis, whatever you want to call it. This is probably one of my go-tos, I think, from last week. So I quite like any run as well, but I'm kind of familiar with this particular UI and stuff like that now. And there's loads of stuff here that obviously it's going to give us information about, but really from an initial assessment point of view, I'm interested in what processes spawn. So in this particular example, you can see here that like there's a new process which gets launched. It has like a weird command line argument as well that's passed to the child process. So that's kind of like evidence of some kind of injection here that I would be looking for in my behavioural analysis, and then further static analysis really when I kind of want to work out how it's injecting into that new process. And the aim here is that I want to dump this process, right? This child process. I want to get access to it. The likelihood is that's the unpack code, or all of the stuff. Or, it's going to have all of the kind of key indicators that we're really interested in. This sounds like this is booting up. So let's have a look and see whether we're going to get anything back to life here. Hey Abdul, how's it going? Okay, Johnny Bot, all good. Right. Do I have the ability to copy and paste into this virtual machine? That's the question. Fingers crossed. What is going on with it? Yeah, this is embarrassing, isn't it? Not even responding to my keystrokes now or anything. Going off. I'll fire up one of my other VMs if it doesn't come back to life shortly, so apologies. So yeah, anyway, I guess from here, there's not much in the kind of output of the sandbox that really gives me a clue as to how the process is being injected. You can probably go through all of like the strings and stuff or the imports and try and guess your way through, but really we want to kind of look behaviorally at this malware. And there's a few breakpoints you can set which are really common for when like a process will write into a different process's memory or allocate virtual memory, that kind of thing. And in this particular instance, it's quite straightforward actually to get to this process. Hopefully, so we'll see it. So yeah, let's have a look, man. Yeah, Darren, I agree. It's probably been a while since I've rebooted this computer, to be honest with you. But might be the problem. I think actually when I start streaming, oh sorry, my cup is right in the way of me, I beg your pardon. When I start streaming using OBS, it uses quite a lot of resources on my machine here, and I think that's probably half of the problem. My MacBook can't really cope. I think it's only got 8 gig of RAM, which isn't great. It's a few years old now, so time for an upgrade. I keep giving myself excuses to go and buy one. So. Come on, you piece of shit. I wonder if I can even run stuff on this thing. Hi Michael, how's it going? You haven't missed anything yet, don't worry. So I can run stuff, okay, so it's alive at least. Let me success, we're in. Alrighty. So first thing we want to do, let me get my tools fired back up here. I usually run just a few behavioral monitoring tools. So the first one I always start with is process monitor. I feel like I'm repeating myself over previous streams here and stuff, but that's what I always do. What am I doing? So I usually from the outset set filters for where the processes create and exit, because I just want a kind of quick view. Let me stop this for 1 second. I want like a quick view on like what processes are spawning and what's happening when I run this malware. I tend to run process hacker as well, and that's just so I can have a kind of live view on what's going on the processes, and if necessary I can dive into the memory of each process, and like just have a look in the strings in the memory just to see whether there's anything useful there, so we'll have a look at that in a second as well. I also run Burp Suite, so I proxy my. We start later, definitely. I proxy my network adapter through Burp Suite, just so I can capture anything which is proxy aware through the HTTP history. I definitely don't want to update. Let me start Burp Suite off as well. And then also, because not everything will be captured through the proxy, I tend to run either Wireshark or Microsoft Network Monitor, which is my preferred option. So take Intercept off, and then I just kind of keep an eye on the history tab here. So let's put that over there. So, all good. Let's get this going as well. I don't want to update this. So we'll start monitoring network traffic. So the first thing I want to do is just kind of run it and see, obviously what happens from a process point of view more than anything else. So let me make sure this is running. I always forget this one, capture events. So that's ticking away. If we double click, hopefully it'll do something bad. You can see obviously it exited the process pretty quickly. And now I've got this service which is spawned called Pixel Pink, and that's because I'm local admin on this machine. So for Emotet itself, if you're a standard user we don't have admin rights, then it will persist in the registry via the usual kind of current version run key and drop itself into a user writable location. Just copy the exe over. But if you're an admin, it will start itself as a service and persist in system32. So yeah. So you can see it's deleted itself from my downloads folder. What I like to do is if I just stop capturing the events for 1 second, you press Control and T in Process Monitor, you'll get the process tree. You make it a little bit bigger, and we can see the kind of parent-child relationship between the processes, and we can see here that there's a child process of the main parent which we launched. Excuse me. And then that's finished, right? So the green bars tell you whether or not the process is still going. It launched Pixel Pink, and you can see the path of that binary was in the system32 folder. I seem to have hiccups all of a sudden as well, just to add to the live stream shenanigans. And then that in turn has also injected into a child process as well. And actually, what you find is this initial parent is an exact copy of this binary here in system32. So if we were to take like an MD5 hash of those two executables, so the one that I copy and pasted and this one in system32, they would be the same. And so it just relaunches itself with admin rights, right? With system privileges within as a service. So that's what we got going at the moment. If we have a look in Burp Suite, let me see, did we capture anything? I don't think we did. And then also if we go into Microsoft Network Monitor, let's have a look and see. You can see that we do have Pixel Pink in Network Monitor, and we've got an IP address here or several IP addresses that it's communicating with. So that's cool. So we've got some network indicators, right? So the first one is this 190.117.206.153. So that's cool. Let me stop that capture because we're probably not interested in anything further from that. You can also as well, what I like to do, like I said before, is in this process hacker view. You can have a look in the strings in memory using Process Hacker, and you can see as well. Actually, when you do that straight away, there's like an IP address. You can pull out some pretty interesting IOCs from the strings in memory, basically. If you wanted to get a bit more creative, what I tend to do, let me just bring it up here. It's because I'm rubbish at regular expressions myself. Let me get rid of this screen. You saw my screens out. Hang on a minute. Yeah, back here. Let me get on CyberChef, and then you can put like regular expression searches in those memory strings. And like I said, because I'm like rubbish at regular expressions myself, I just use ones that are built in. So if I want IPv4, I'll just copy and paste this regex, which I could definitely never write. Oops, closed it. And so you get false positives because it's a regex, right? But you can see it'll just match stuff that is an IP that has an IP address in the strings. So it's a bit easier to pluck them out of memory if that was your first port of call for forensics. So here's another one here that you could pluck out, etc. So that's cool. So one of the things we'll do is I'm just going to make a note of the first IP address. In fact, I'm going to write it down just because I'm going to forget it otherwise. I can find a pen. Ah, yeah. 1 second. 153, right? Okay, cool. Because what we'll do is we'll go hunting for that in the binary shortly. Let me just make sure I check my chat right. 1 second. What's going on? All right, cool. So what we want to do is, first off, we need to have a look at this malware in a disassembler. So we're going to stick it into Duncan's favorite tool, I imagine, which is x32dbg. So we're on a 32-bit machine here. So we'll use x32 as opposed to x64. Let me just close these off a second. We're not capturing, that's good. Let me get the binary back in my downloads folder here. So let's stick it in a disassembler and see what we see basically. And the key is to work out how it's writing into this new process. And if you watch, I won't take any credit for this at all because I learned so much from these guys. But if you watch OA Labs, if you watch their channel on YouTube, they can teach you so much about unpacking malware and process injection and stuff like that, and probably way more than I could ever teach anybody. So definitely go and check out their channel. And one of the things that they quite frequently will recommend, or there's a list, if you like, probably a handful of breakpoints on API calls that you should look out for. Set your breakpoints on particular API calls to look for indicators of process injection. And I guess the problem is that there's so many different ways that malware can inject into a different process and unpack itself. I guess off the top of my head, I guess there's the two that I see most of. Firstly, are process injection, which is what we'll have a look at here. But then also more of a classic DLL injection technique, which will use like load library and create remote thread. And so it will write into the virtual address space of another remote process, which it will probably enumerate on the target machine, and it will write the address of like a DLL, for example, that it wants that process to invoke. And so all it's doing is writing the address of that DLL and then creating a thread in that remote process to go and load it. And there's a challenge with that, as you might have guessed, that you have to kind of write the malicious DLL to disk in the first place, which is a little bit tricky with respect to antivirus and EDR tools and stuff. So this injection method is a little bit more stealthy in as much as it's happening in memory, so nothing is actually being written to disk. But a couple of the API calls that you should definitely set your breakpoints on. Firstly, create process internal W. So we can do that here. So let's skip to the entry point. Oops, shit! I had to run it. Let me go back. So if we set a breakpoint on create process internal W, that's one of the API calls which will commonly be called when a new process is created. And then once that's there, you can see some attributes around the new process that's being created, and you can see the kind of code that in and around the malware that it's what it's going to do next, basically. What's it going to write into that process and what have you. I hope I don't have the same problems now of writing to my virtual machine again. We'll see. Phew, we didn't. So let's get this into our debugger again. So you can set your breakpoint on create process internal W, and then one of the other ones I like to set the breakpoint on. If you press Control and G, you can follow an expression here in the debugger window, and it's on virtual alloc. And actually, what we want to do is set our breakpoint on the return from virtual alloc. So we don't actually want the call to virtual alloc, although you could do and then just step through the code. But it's easier if you just follow through these instructions. You can see there's a jump and then there's another jump. And if you scroll down here, you can see this is the return of the actual call, where it says return 10. And the return from virtual alloc will return a value in the EAX register. And that value will be what we're interested in dumping out. So it's going to be the address space of where this buffer of all this data is going to reside. That's going to be written into this virtual process. So that's probably what we're really interested in. So we've got our breakpoint set on that as well, and hopefully it'll give us something interesting to go and play with. So when we press F9, we can see that the malware is running now in the debugger, and we can see that it's hit the breakpoint that we set here on in kernel base, which is the return from virtual alloc, and the value here in EAX has been written, so we can follow that in the dump. And we can see that at the moment, the contents of that address space is all blank. It's all 0. So nothing's been written just yet. So if we press F9 again, you can see that now there is actually some stuff that's been written, but it doesn't look like a binary or anything interesting. Well, at this point, what I would do, one of the kind of tricks, if you like, is you can, instead of stepping through the rest of this code, because this isn't the actual malware code, this is in kernel-base.dll, we want to go back to the user code and see what the next kind of instructions are. So you can see here, there's quite handily this run to user code option, Alt and F9 in x32. So if we press on that, we can see here's the call that's just been made. So there's a few things been pushed to the stack here before the call to virtual alloc, which was in EBP. And then we're on this instruction here, so our instruction pointer is pointing to these instructions here, where there looks like a buffer being moved into the ESI register. And as soon as I see that, it's a good idea just to kind of poke around, so you can follow in the dump the address of that buffer, in this case EDI plus 54. And sometimes, if I'm honest, sometimes you just get a bit lucky. So sometimes when you dump stuff out of the return from virtual alloc, it'll be a real nice clean PE file with an MZ header and all the rest of it. But actually what you can see here is there was just some stuff, that maybe was encrypted, I don't know, or was just a blob of data. I have no idea what it was. But when we took a step further, we can see that in and around the code, there's some movement of memory, or contents of memory being moved about in the code. And if you just start poke around and dump it out, you can see that actually what we looks like we've landed ourselves in here. Scroll up a bit, we can see we're in the header of a PE file. So we can see an MZ header, we can see the DOS stub, we can see the section table, all the rest of it. So at this point, this is what we want to dump out, and then we can hopefully do some analysis on what this PE actually is. So the way we would do that in this particular case is we can follow in the memory map where that all of that code resides, and it's here and highlighted in grey, and we're just going to dump it out. So we'll dump the memory to file. Let's stick it on the desktop for now. Oops. Come on. Let's call it stage2.bin, whatever. But you'll notice that we weren't at the top of the memory space there. So if we put it in a hex editor, for example, it's all of this noise, all of this shit above our MZ header. So if we search for our MZ header, it's down here somewhere. So actually what we want to do is we want to select the block. We start at 0, end at that portion of junk that's before our MZ header, just delete it. So we can see that our binary now starts with the MZ header, this, the dot stub, etc. And we'll just save it. It always creates a backup, and I always get annoyed because I feel like it's polluting my desktop. And so we've now got stage 2, and if we use PE Studio, we can hopefully see that this is a valid binary. And we got indicators as well, which is good. So suggesting that we have actually found something, obviously malicious, but something which is a proper MZ header and a proper file that's going to work. But you can see that actually there's only one library, and there's only one import, which is a bit weird. And it seems like there's still either some pack in there or some obfuscation that we need to kind of work around, and not many strings either. But fear not, if we stick this in a debugger. Again, let's get to the entry point. One of the things you'll see, we are on our normal function prologue of push EBP and move ESP into EBP, but then here you can see that there's a real large where we're subtracting 420 from ESP. We're creating a lot of room on the stack for a lot of variables. A lot of local variables to this particular function, and that's interesting. That's quite a large number of variables, and there's a couple of calls here to some subroutines. And if you even hover over them, or you can go to them, press enter, you can see that there's a load of static values here, a load of strings being moved about, and these are quite common. When you see stuff like this, it's quite common that these are actually APIs, Windows APIs that are being dynamically resolved at runtime. So the malware will, have this hashed version, which is what this kind of string looks like here, of what the API call is, and it will pass it through some routine where it will actually decrypt what that hash means. So actually, I'm not actually that bothered about working out how that works. What you can actually do is just, if I breakpoint on the instruction after those two calls, watch what kind of happens down here to the rest of the instructions. You'll see some API calls appear because they would have been decrypted and resolved. So if I press F9, you can now see this is a call to get module file name, and then we've got some printfs, get command line, etc. So we now know that the API calls have been resolved, and in fact, if you go into, we've now got more imports and stuff like that, and we can start poking around the malware a little easier because we can see actually what kind of calls are being made. In this particular instance, actually what this code is about to do, it's going to start looking on the command line, and it's going to start comparing the length of the command line and just looking to see what command line parameter has been passed to it. And if you remember, where's our sandbox gone? Here. So it's looking to see whether or not there's a command line parameter been passed to the child process. And it's probably, I would imagine, I don't know this, but it's probably some kind of check the malware does to make sure that this second process that's running is actually as a result of it being spawned from the parent, as opposed to us statically analyzing it and just kind of piecing our way through it. But our goal here is to really understand or extract the network indicators from the sample. And if you remember, we obviously ran it and we saw some IP addresses in the binary. And so one of the things I wanted to look at is to see whether or not we could find where the config resides within this particular, what is now the unpacked sample. So we had let me go back here just to bring it up on the screen for you. So just ignore this. I guess I'm going to use this as a bit of a text editor for now. So that was the IP address of the first communication to the first C2 IP address. So what we're interested in is if we convert these values to hexadecimal, which I don't know how to do off the top of my head, so I tend to use rapid tables. So the key is if we do this in reverse order, because if you can imagine that each of these octets in the IP address are going to be on the stacks or be read and pushed to the stack somehow and read by a function or passed as an argument or whatever in the malware, but they're going to be passed in reverse order, so to make sure that they're transmitted in the correct order. So the .153 will be the first byte that's passed into whatever function that uses it, or it's going to exist on the within the binary. So we'll convert the we want decimal to hex, don't we? So convert 153, so that's 99 in hex. So that's good. So we want 99, and then there's 206. CE 117 75. Okay, and last one was 190 BE. Okay, so that's like a pattern of text now that we can go looking for. So if we go into the memory map, what you can do, if you just right click anywhere, you can find pattern, and you can find ASCII or Unicode or hex or whatever. So in here we're going to do, I don't want to do that, do I? We're going to do 99 CE 75 BE. Hopefully this works. And we got a result. So obviously that's the IP address in what you know, to humans would be reverse order. But if we double click that, oops, shit. Go back, sorry. If we right click it and follow it in the dump, we can see here that the IP address is here, and we're in what we will see shortly. If we right click this kind of area and follow in the memory map, you can see that we're in the data section, which is quite nicely labeled here in x32 is initialized data. So when the binary is compiled, you'll have various sections within the PE. The text section, as you can see here, is where all of the executable code resides. There's some read-only initialized data, which tends to be like hard-coded strings, stuff like that, and then initialized data as well, which is where we find ourselves at the moment. So here's our IP address, and I know full well there's obviously more IP addresses because we saw a few of them right in our behavioral analysis, but we want to kind of be able to pluck out all of them. And if we take the next 2 bytes here, so we can see BB01. If we just convert those, so we'll go from hex to decimal. Oh, forget my endingness. 01BB. That's port 443. So that was the port that the IP address was communicating over. So that's really interesting. And you see as well, what you've got to kind of have the mindset of right now is, okay, well, I've got an IP address which takes up 4 bytes here, and these are in. You can see that obviously we got blocks of 4 bytes, what have you. The next 2 were the port number, and I don't know what these next 2 bytes mean, but if you can imagine that we're going to see a repeating pattern here, I can see there's 4 bytes here, and I've got BB01 again, and BB01 or 01BB, depending on your endianness, is port 443. So you can imagine that these string of bytes is going to be our next. If we copy that, that's going to be our next IP address. So let me just paste that here for now. So remember though, we need to read it in reverse order. So we'll start with CB. So that's 203. And then it was 63, which is 99. BB 187, and then 89, which is 137. So that's our next IP address. You can see how like laborious or boring it is to do it manually. So what I thought would be interesting is to script this up. So what we can do now is if we go back to our memory map, we know that the config is in the data section. We can just dump this data section to disk. Stick it on our desktop here. Data section .bin. I'm just going to copy it back over to my host here, because I'm going to run something on our host. But let me show you. I knocked together a little script. Shamelessly, I've put it on my GitHub. I've started a little folder on my GitHub here, which is just for hacks, which just bits of script and code and what have you. But I wrote this quick bit of Python, which will, if we look through the code real quick to kind of talk you through it, The first thing it does in its main is it just reads the file that you pass as an argument. So if we pass it the data section memory dump, it reads it in binary, so it's going to read the bytes in that file, and then it just looks. It performs a regular expression lookup, right? So I've put a few common ports here that Emotet uses. So it uses 443 and 80, but also quite commonly uses 8080 and 7080, and there are others as well. So I've listed them here. So we saw BB01, but due to the endianness, right? So it's going to read in 01 first and then BB. So that's port 443. But you would look for the byte pattern of BB01, or if you were looking for port 8080, you'd be looking for 91F, etc. So it's going to read the bytes, and it's going to look for those matches. So in actual fact, what it's going to look for here, these 4 dots means it's going to look for 4 bytes, and they can be anything, and then also followed by the next 2 bytes, and they can be one of those port numbers. And then it's going to find all of the matches, and then I will caveat the whole thing by saying I'm not a Python developer at all, and there could be 1,000 different better ways of doing this, but this is just how it worked in my brain. But we're going to iterate through all of those groups, all of the matches, and then just keep an array, keep a list in Python of the of where the offset of those matches start. So we're gonna have this big contiguous block of bytes. It's going to find matches all over the show, but what we actually want to do is find out where the first match was and where the last match was, and we're going to take that chunk of data, and that's going to be what our proposed config is going to be, a C2 config. So here's where we get the first match in that list, and then we'll get the last match in that list as well, but then make sure that we read the 8 bytes past it to get the last IP address. And then we just pass it. So we get bytes 3, 2, 1, and 0. So the first 4 bytes in reverse order, which will be the IP address. And then bytes 4 and 5, which are the 5th and the 6th byte, are going to be the port. So we just join them up here. And then print them out to the screen. So if I get... I got a terminal window somewhere here. So... let me get my data section in my right folder here, and then we'll run the script and hopefully it'll work. Right, so we got my data section. So if we run it, there we go. So we got the first one, which is what we saw in our behavioural analysis. The second one, etc. But then you've got all of, we've got some weird ports in there as well, like 993 and stuff, and that's all stuff that's not, port 993 was not in our regular expression filter in that Python code, but excuse me, because we've taken that kind of contiguous block of, like, we've gone for the first match and then the last match and just taken everything in between. We've managed to pluck out a lot more IP addresses and a lot more indicators from that particular sample. Made it quite easy for ourselves. So that's on my GitHub. So please feel free to use that. It does rely on the fact that you need to have unpacked the sample first and then dump it with the data section out and just feed the data section. But as you can see, it's been pretty trivial to actually do that. So. No doubt, as I said, there are thousands of ways of doing that more effectively, but it seemed to be the way it worked for me. So, right, let's have a look at the chat anyway. That's majority of the content I planned on going through. So let's see what your kind of questions are. Let's have a look. A lot of people asking about OA Labs. Yeah, OA, you guys have got it right. So OA Labs at Hercore on Twitter. The guys are awesome. They've got plenty of samples where they show some quite interesting unpacking techniques and stuff like that. I'll show you. In fact, what I will show you real quick. I did have another sample of Emotet, which was a little cleaner than that one I've just shown you. Actually, let me get it on here. I found it in a blog post, but it seems to be a bit easier. My virtual machine lets me paste. Remzo from Bosnia, hey, how's it going? Thanks for joining. Let me redo this again. Elmar's on the stream. Hey dude, how's it going? Lane likes my Python. Thank you for that. I tend to write uber commented code for my own benefit more than anybody else's as well. So, but hopefully you can follow along with it and understand what it does. Right, but yeah, so this is another Emotet sample, but you can just see super quickly that this is actually a little cleaner to unpack. And this tends to be more of what I would see in the wild a lot more. So if we set our breakpoint again on the return from virtual alloc, so we just jump through the code here, find the return, F2, press F9 to run it. We've now hit the breakpoint. We're on the EAX register, so that's the value we're interested in following. You can see there's nothing in there at the moment. And press F9. And boom, there you go. It's really easy, right? We're at the top of the memory section. We've got an MZ header. You can just follow that in the memory map, and then you can just dump that to the file. Nice and easy. When it decides to wake up. And then you put that back in here. You can see the same two calls. So, to the API resolution. So if you're interested in knowing all about that, just run past it, and then you've got all of your APIs have been resolved. And then, yeah, again, so in here you could dump the data section. Call it blog data, because I found this sample on a blog post. Let me copy it into my folder. I'll get back here. And we can see this one's got way more C2s on this one. 61. It's pretty good. So you can see like port 21 being used, port 20. It's weird, isn't it? But all of these, so if you're in a corporate environment analyzing Emotet, you really want to quickly find out the network indicators you can block, because it's such a prolific piece of malware. It will try everything to route around your network internally and obviously externally communicate back to its C2 infrastructure. So yeah, Advert, thanks for the question on the process injection. I think so. Super quickly, what I talked about earlier was, if you run the sample from a behavioral analysis point of view, so stick it in a sandbox or use process monitor yourself. You can see here that the sample that we looked at spawned a child process, of the same name and stuff. So, that would immediately lead you to think there is process injection at play. And therefore you need to go and poke around how it's doing that in order to dump out that process. What I would also say as well, there are plenty of samples that I've analyzed over the years that I can't work out what method is being used to inject into a remote process or what have you, or the API calls are undocumented and I've never heard of or what have you. But an amazing tool is called PECIV, if I spell it correctly, by Hasherazade. Here, not an actual sieve, as Google would have you believe. But PECIV is amazing. She's a genius, this lady. But this is a tool which will help you analyze malware on your system, but also if you have a process in memory, it can dump it out for you cleanly as well. So definitely worth checking that out. But yeah, stuff that's been injected into a different process doppelganging, etc. This is an unbelievable tool. I might actually cover this in a different stream because It deserves more than just a few minutes kind of talking about it, but check it out in the meantime. So yeah, that's what I kind of covered anyway, with respect to injection. As I said, because it's such a vast topic, and I could probably think of 10 different methods right now on how you would inject into a different process, or even self-injection as well, which is really, really common. But you should, there's so many videos on YouTube from OA Labs and others as well. You should go and check them out. So, all right, before we wrap it up, then what else we got in the chat? Yeah, it's all good chat. Hopefully I've covered most of the questions there anyway in what I've been saying. So, but yeah, thanks for joining me. Excuse me, and then also thank you for putting up with the problems with my virtual machine for the first few minutes as well. So we managed to get our heads around that. But yeah, hopefully that's a useful tool that people could use to dump the configs for Emotet. That's the kind of mindset I approach when I'm unpacking. I tend to have always have the mindset of when I'm unpacking malware, I want to do it for a particular reason. I don't just want to unpack it just because I can see it injected into a process. I want to actually unpack it because I want to go looking for something specific. And in this case, it's obviously the network indicators that we're interested in and stuff. So that's how I approach it. Cool. Oh, thank you for the kind comments as well, guys. Really, it really is good. I think I'll wrap it up here. I'm going to get myself some dinner now, and probably see you guys next week. So thanks for joining. Thanks for stopping by.